Welcome back. In our last class, we introduced the force on a moving charge in a magnetic field, the Lorentz force. Magnetic fields are different from electric and gravitational fields in that the magnetic fields are about changing the direction, about changing the orientation of an object rather than applying directly a force. So it is useful to compare again what happens as a charged particle moves through an electric field and how a charged particle moves through a magnetic field. In an electric field, on the top of this figure here, we have a uniform electric field that is pointing down, and a positively charged particle moves through the field to the right, and the force points down. It doesn't matter how fast the particle is moving to the right, and the electric field just bends the charge down. Notice this is a uniform electric field because the field lines are evenly spaced, and the force is pointing down because the field lines are pointing down, and the charge is positive. This is just like the projectile motion problems that we did back in 201. The x component of the velocity, the motion to the right, is constant, and the particle accelerates down, so it curves down and with increasing speed in the downward direction. Notice that even if the charged particle is not moving, the particle will still experience a force. So in that case, the velocity will just be straight down, and the particle will accelerate down. The only complication is what the charge is. If it is positive, the particle will move down with the electric field, and if it is negative, then it will move up in the opposite direction of the electric field. In the case of a magnetic field, now the orientation of the motion matters. We have a positively charged particle moving to the right with the magnetic field pointing down. So, as the particle moves to the right, we find that the direction of the force using the right-hand rule. The velocity is pointing to the right, so our pointing finger points to the right. The magnetic field B is pointing down, so that means our middle finger points down, and so that means that our thumb then points into the page. So that means that into the screen. So that means that when it is going into the screen, after it's turned here, now our pointing finger points into the screen, our middle finger points down for the field still, and our thumb will now point to the left. Once it goes to the left, then now our pointer finger will point to the left, our middle finger is still down, and so the force is now out of the page. And lastly, once it's moving out of the page, middle finger stays down, the force is now to the right, and so now the particle is moved in a full circle. This is because the magnetic field is about changing the orientation of the magnet, so the charged particle makes an orbit through the uniform magnetic field. This is also often called cyclotron motion, where a charged particle going through a uniform magnetic field has circular motion. Notice we are not speeding up the particle. The force is always perpendicular here, so the work done is zero, so the kinetic energy remains the same. But the velocity's direction is changing very much. Again, this is quite different from the electric or gravitational field, because instead of the field accelerating the particle, it is turning, it's deflecting the particle. Okay, so if we look from the top down, the charged particle is turning around and around in a circle in what we call a cyclotron motion. In this case, the magnetic field is pointing out of the page, right, our circle with a dot, so that means that at point 1, the positively charged particle is moving to the right, and so the magnetic field is out, so our middle finger points up, so that means the force is pointing down. So then as the particle turns, the force remains at a 90-degree angle from the direction of the motion, so the particle loops around in a circle. So as that particle goes around in a circle, that means the magnetic force is supplying the centripetal force that makes the particle turn in a circle. In our case, the force is QVB sine theta, where Q is the charge, V is the velocity in meters per second, and B is the magnetic field in Tesla. The angle here is always 90 degrees because the velocity is in the page and the magnetic field is out of the page, so that sine of 90 degrees is 1. So that simplifies, and we can set that equal to the centripetal force here. So that means the centripetal force is mass mv squared over r, where m is mass in kilograms, v is velocity, and r is the radius of the cyclotron orbit. We can rearrange this to find the radius for all charges in a perpendicular uniform magnetic field and get that r, the radius of the orbit, is equal to the mass times the velocity divided by the magnetic field and divided by the charge. So the faster the particle goes, or the more massive it is, the larger the radius of the cyclotron motion, and the larger the charge, or the magnetic field, the smaller the orbit. This effect is important in a number of applications. In high-energy physics, the way we identify high-energy particles is to put a strong magnet in a cloud chamber, then we watch as high-energy particles fly through. The particles leave a vapor trail as it moves through the chamber, and you can tell the charge of the particle by the direction that it curves. So if it's positive, it will curve one way. If it's negative, it will curve the other. Also, if you're lucky, you can tell the mass-to-velocity ratio. This is extremely important in mass spectroscopy. So there you accelerate a molecular ion through an electric field or a molecular fragment, and so you control the kinetic energy. And from that, you can then find the mass-to-charge ratio of either a molecular ion, or if you fragmented it, you can determine the molecular mass of the fragments, allowing you to determine the structure of a molecule. Okay, so now we want to look at the radius of a particle. We have a charged particle with a charge of 2 microcoulombs with a mass of 4 × 10⁻⁷ kilograms, a speed of 0.5 meters per second, and it's moving perpendicular to a magnetic field of 0.3 Tesla. So we want to know what the radius of the cyclotron motion is. This one's pretty straightforward, right? Kind of a calculator test question. So you plug in your values here, and you get that the mass times the velocity divided by the magnetic field and the charge gets you the radius, which comes out to be 0.33 meters in this case. Notice that if we increase the magnetic field or the charge, the force gets larger, and when the force gets larger, the radius gets smaller. So as the magnetic force gets larger, then that centripetal force gets larger, so the radius decreases. On the other hand, the faster the particle, or the larger the radius, and then the more massive it is, the larger the radius. All right. Okay, so another kind of moving charge is the electric current. So what happens when we have a current moving through a magnetic field? So in this case, our current, the direction of motion of the positive charges is up, and the magnetic field is pointing into the page. So we use our right-hand rule to point our pointing finger up and our middle finger into the page, so the force on the wire will point to the left. When the current loops around and points down, then our pointer finger points down, our middle finger is still into the page, and so our thumb now points to the right, so our force points to the right here. So to find the magnitude of the force, we use that the magnetic field times the current in amps times the length of the wires, L in meters, times the sine theta of the angle between the magnetic field and the current. So if the current and the magnetic field are aligned, then the force is 0, and if they are perpendicular, the force is at a maximum. So this is just like the Lorentz forces we've just been talking about. Notice that this is the same thing we were doing before, right? Before it was the charge times the velocity of the charge times the magnetic field. Here it is the current, so charge per time multiplied by the distance that the charge travels. That means it's charge times distance divided by time. So here, in the case of the current, the distance is held constant, and the question is how much charge moves that distance, but the units are exactly the same in both cases. So this is really just the Lorentz force again. We're just looking at it in a slightly different way. So yeah, for these you use your current in amps, your length in meters, and the magnetic field in Tesla. Okay, you have a couple questions to do. Next, I think I'm going to do a review of the right-hand rule, because I'm a bit worried you've only really seen that once, so I'm going to do a careful walkthrough with that, and good luck with your next couple of questions.